Hello, my name is Andrei Kvapel, and today's presentation about Kubernetes is a new Skynet, or the rise of Kubernetes automation. In this presentation, I'm going to show you some sort of technologies we used for building our own platform, such technologies as Talos Linux, KubeVirt, Kamaji, and things like that. I will explain how they works and how we used actually our approach is how we use them to prepare the platform. A few words about me. I start my Kubernetes experience for a long time ago. Since 2023, I founded new company for developing open source platform for provisioning managed services. The main target audience for this product is hosting providers or internet service providers. We help them to extend their profile with managed Kubernetes services and managed databases, queries, and things like so. So let's talk about how you can build your own platform, and we can split this presentation for 4 different topics. The first one is Kubernetes on-prem challenge. And first, let me ask if you like using Kubernetes in cloud. I guess yes. But there is a joke that there is no cloud, it's just someone else's computer. So if you're internet service provider, or if you're just ordinary Kubernetes user, if you're ordinary Kubernetes user, you just work with smallest Kubernetes part, actually Kubernetes API. The rest part are usually done by cloud provider, and they should solve a lot of things like how to provision bare metal nodes, how to configure persistent volume provisioning, networking, kernel updates, etcd management, and things like so. So if you're a Kubernetes user, you don't want to take care about this. But if we talk from the cloud provider perspective, you should know how to do that the best way. So my presentation is more about for internet service providers if you want to build your own cloud for Kubernetes. And let me explain how it works. So if you work with Kubernetes in cloud, you usually work with such scheme. When you have Kubernetes control plane, you communicate directly with it, and you have worker nodes, persistent volumes, and load balancers, which are balancing the load to the traffic to your workload. You can scale this cluster down, you can scale this cluster up with autoscaler. You can even remove all of your worker nodes, then run them again. Your application will continue working after the nodes are created. The same persistent volumes which are managed externally, and the same load balancer will continue routing this traffic into the worker nodes which are handling your workload. So nothing will be broken, and this scheme is very granular and it works very well. But in case if you want to create your own cloud for Kubernetes, you have few options. By the way, if we talk about Kubernetes on bare metal, we usually means that we have some bare metal nodes and we install Kubernetes on them. You can use various tools, for example, K3s, or KubeAdm or KubeSpray. There are a lot of options, but instead of this amazing scheme on bare metal, you usually get something like this, and this scheme is a little bit more complicated, I would say, because it have no convenient management. The updates are quite painful because the workloads running on these bare metal nodes, it should be prepared to be running in such way and be ready to migrate to another nodes, handle high availability and things like so. And of course, those bare metal nodes are difficult to scale. You might have some options to configure autoscaling for bare metal nodes, but it is not so flexible like for virtual machines. And of course, you have no multi-tenancy. Kubernetes is nice platform, but it was never considered as platform like OpenStack or OpenNebula to implement hard multi-tenancy model. Hard multi-tenancy means that your tenants cannot affect each other they actually knows nothing about each other and can affect each other. In Kubernetes, we have soft multi-tenancy model, and it might work not so very well on bare metal nodes when you let totally different users to access your cluster. So in this way, if you're trying to solve this, usually means that you need to have separate Kubernetes cluster for each development team, for each project. And if you're trying to solve this case, you usually become to the idea of using private cloud. In this way, you can use OpenStack to bootstrap OpenStack on your bare metal nodes and then start spawning multiple Kubernetes clusters right in it. Just for Kubernetes for every project, Kubernetes for a development team. In this way, OpenStack provides you a really nice level of isolation. But the problem, who is responsible for OpenStack? If you want to keep OpenStack in your infrastructure, you should know that it is very difficult. It consists of many microservices which are connected to each other, and it might be really difficult to manage. It usually means if you have OpenStack in your infrastructure, that you have dedicated specialists who are responsible for updating and maintaining this OpenStack system. And now I just want to say that there is some other options. So you can use Kubernetes to run Kubernetes. For now, nowadays Kubernetes already have everything need to run virtual machines and other virtualized Kubernetes clusters right in it. So you can replace your OpenStack with ordinary Kubernetes distribution and start creating separate tenant Kubernetes clusters in it. So we even call it like management Kubernetes cluster. The cluster you install on bare metal, that's actually a Kubernetes cluster for which your infrastructure team is responsible. And you can have multiple tenant clusters which are running actual workloads, and you can just cut separate Kubernetes cluster and give to your developers. They will be happy to use it. This scheme works fine because first you have a same ecosystem for both. You can use the same tool set, like you can use Helm or standard approaches like CI/CD for deploying the workloads on both and managing both clusters. Here we have really hard multi-tenancy. So since our clusters are running in virtual machines, that allows you to isolate the workloads between tenants, and they can't affect each other. The tenant clusters implement the same cloud pattern. So you have Kubernetes control plane running separately, you have separate worker nodes, separate PVs, and load balancer. That works pretty fine almost for every application. And management clusters still use this scheme where you have stacked storage and load balancer and control plane. But for now, it is not a big deal because this cluster runs only a certain set of workloads, and you can be sure that they can handle this kind of working in this kind of scheme. So it is usually responsible only for running virtual machines, Kubernetes clusters, and databases as a service. The rest stuff like user-faced workloads, they usually put to their own Kubernetes clusters or their own virtual machines. In this way, we decided to create a platform which would allow you to share our experience by simple box solution which you can get and install on your own hardware. So the main idea of our platform is that you can take a bunch of your servers and simply transform them into intelligent system where you can order managed services like Kubernetes as a service, Postgres as a service, virtual machines, and things like so. Those services already have monitoring configured, and you can interact with the platform using ordinary Kubernetes API. This is how it looks like. So we have dashboard with the tiles and some applications which you want. You can just choose them, click and install. For example, if you want virtual machine, You set some parameters. Every parameter also can be defined in YAML form, and then it gets deployed to the virtual machine in Kubernetes itself. Now let's talk about how does this work. We can split our platform for 4 different layers. On layer 1 we have operating system and hardware. That means on this layer we're managing Linux kernel, the basic system, and also this layer is providing us Kubernetes, the main Kubernetes API which we can use for deliver all the REST components. The REST components we use is actually storage. We use LinStore for this, networking based on OVN, and virtualization based on KubeVirt. On layer 3 we have operators for provisioning our databases, cluster API, and monitoring. On layer 4 it's more likely user face layer. We have this amazing dashboard where you can click and install some applications like virtual machines, databases, and Kubernetes. So the layer 1 is done by Talos Linux. It is smallest operating system dedicated for installing Kubernetes. It is very interesting because it have no any binaries inside. It is purely written on Go. It have Kubernetes similar API, and it allows you to configure your machine right the similar way like you configure in Kubernetes. The rest layers like layer 2 and 3, they are handled by FluxCD. So we use FluxCD and deliver Helm charts. We have system ones and we have application layer, layer 4. It is also backed by FluxCD, but it also have our own customized Kubernetes API server, which shows all of these Helm charts as Kubernetes objects. Let's talk about the layer 1 and Talos Linux itself. And let's switch to the next topic, hardware and operating system management. Let's say you have infrastructure. It could be virtual machines. Those virtual machines can be running in cloud or on-prem, or that could be bare metal servers itself. Talos Linux has ready-made images for everything. So you can use some providers, for example, Proximus or OpenStack. You can just simply download Talos Linux image, import it, and start using immediately. The only thing you need to do afterwards is just to apply configuration to this running Talos Linux system. In case if you want to use bare metal nodes, you can use some more basic methods like ISO installation or PXE booting method. You can also try Talos on your local platform like Docker. It can work inside of your Docker, but it is more likely for development needs. So if you want to use Talos Linux, let me explain how it works. You just boot this image in your machines, and then you can configure it with single configuration file. This single configuration file looks like this. It consists of 2 sections: the machine section, which describes specific machine, and the cluster section, which describes the configuration for a whole cluster. In machine section, you can specify the type of machine, certificate settings, networking settings, and disk to install. In cluster section, you can specify control plane for Kubernetes, the same as certificates for Kubernetes, various components configuration like API server, kubelet, etcd. And afterwards, after you filling all of these settings, you can just use talosctl, the similar tool like kubectl, and apply this configuration to the node. So this node, after applying this node, get configured. They're similar to Kubernetes controllers, which moving the real state to desired state you described in the configuration file. So if you want to bootstrap the whole cluster, you usually need to run commands like talosctl gen secrets. It will create secrets file with all the secrets for your cluster. And then you can use this file for generating configuration for the other nodes. So you can run command gen configuration with secrets, and you'll get 3 separate configuration files. First is talosconfig. This is pretty similar to kubeconfig you can use to access Talos API itself. And you have two examples for control plane node and for worker. If you want to bootstrap your node, you can just apply this configuration using talosctl apply command and specify the node where you want to apply this configuration. So if you want to bootstrap the cluster, you have to apply the configuration to multiple nodes and then run talosctl bootstrap command on one of the node. It will actually initiate the new etcd cluster. So the nodes will find each other and they will start Kubernetes cluster. So you can actually access it. If you want to update some node, you just apply the configuration again and run talosctl upgrade command. It will gracefully remove all the workloads from the cluster, upgrade itself, and then join back to the cluster. Okay, how can we access this Kubernetes cluster? In Talos configuration, you have this VIP setting. You can assign it only for control plane node for some specific interface. It works pretty similar like VRRP, but it is not VRRP. It's fully controlled in user space by checking etcd state. So you can specify your virtual IP address here. It will create floating IP which will move between the nodes. So in your kubeconfig, you can have this virtual IP address specified. So if you access your cluster, you will always go through this floating IP address. It will be moved automatically every time if you put your node to maintenance, if you reboot, so your cluster will continue to be available. Seems pretty simple. That's probably it. We also found that many users don't want to understand this Talos configuration, they just want to try, and we wanted to automate it somehow. So we built our own method for installation. It's called Talos Bootstrap. It works pretty similar. It actually shell script which allows you to bootstrap your nodes. First, we provide DHCP and Pixie server in Docker images that allows you to boot your nodes. So they get boot Talos Linux into maintenance mode, and then you can use Talos Bootstrap to create clusters communicating through it. Let's see how it works. So after your nodes get booted, it allows you to find all the nodes in the network. You can choose the node, enter hostname, choose disk to install, enter IP address, virtual IP address, and finally you get a configuration file which you just apply to your node. Then it gets rebooted, and then you repeat that every time for every node, and in 5 minutes you can get ready cluster. Also, we prepare our own Talos Linux image, which includes all the needed kernel modules which we use in our system. That actually allows us to create basic and stable layer 1 for our platform. So we can be sure that this layer always consists of needed kernel modules, always running the similar kernel version, so we can be sure that it is stable base for our platform. And now let's talk about the rest stuff. Actually, system components, how we deliver our system components. So usually if you have some system components, such cert manager, rollbar, access control, CNI, monitoring stuff, all of these things can be delivered using FluxCD, and Talos Linux works very well with FluxCD. So FluxCD can take your Helm charts and just simply install on your cluster. Even in Talos Linux configuration, you can specify extra manifests which should be applied to your cluster. The only thing it works not very well because we found that sometimes it might be better to do intentionally rather than providing the configuration such way. So our method is slightly different because we don't use Git. We actually want to make box solution, and we did this box solution and we utilized Flux for that. Let me explain how it works. So we let user to create single YAML configuration after their Talos Linux cluster get bootstrapped, they only create single YAML file. It creates actually the container, and this container contains all the needed Helm charts to use in our system. It also have small script to install Fluxity, and then all the rest stuff like installing components is done by Fluxity. So Fluxity takes those Helm charts from the container and bootstraps and installs them into existing Kubernetes cluster. If we want to update the platform, we just replace this container with new Helm charts, and Fluxity just updates them in a cluster. Very simple. Such way we deliver the storage. Our storage is based on DinStore, which is pretty reliable solution because it works with time-tested technologies like LVM and ZFS. And in case if you need replication, it also can enable it using DRBD. We also deliver OVN, the thing we use for running virtual machines. It allows you to move IP addresses between the nodes, which are ordinary CNI plugins in Kubernetes can't do. So KubeVirt also coming such way, monitoring stack based on Victoria metrics and things like so. So we deliver all the system components using Fluxity. And now let's talk about the most interesting part, how user working with our application. So we have user applications such as managed Kubernetes, managed databases, virtual machines, S3 storage. All of them are listed in this dashboard and managed by Fluxity. But as I mentioned before, we have our own customized Kubernetes API server. We prepared using Kubernetes API aggregation technology. So we can dynamically extend the Kubernetes with new kinds, which are not CRDs. They kind of CRDs, but they not CRDs. They actually simply transcode it into Fluxity resources. You can operate with such resources like virtual machine, Postgres, Kubernetes. But anytime if you create such resources in Kubernetes API, they automatically translate it to Fluxity Helm releases. So in this way, you can simply extend the platform with new kinds. You can use Helm to prepare any application and specify a new kind for it. Let me show how it works. Let's start from the virtual machine. If you create virtual machine, you usually create this kind of resource. You can see we have apps cozy stack IO, this kind virtual machine. In spec, we have some values. After you create this resource, it gets managed by Helm itself. It also creates a virtual machine for KubeVirt, and it is still managed by KubeVirt. And this is very important because Helm does not provide you full lifecycle management. Only operator can provide you, and KubeVirt such operator for virtual machines. If we will take, for example, database as a service, we also provide such opportunities to create Postgres, MariaDB, Redis, and things like so. All of these databases are managed by operators, but our API still based on Helm that allows you to create these standardized options for the users, so they are capable to change only specific parameters, and the more important that you can extend the platform very quickly. So anytime when they create new Redis, it actually creates the resources for this database, and it is still managed by operators. For example, Redis cluster, it creates 3 extra YAMLs like Redis failover for Spotahome operator, the service for accessing, and VM scrape for scraping the metrics. This is how it works. The more interested part, how Kubernetes is organized. Since we provide fully functional Kubernetes cluster, what does it mean fully functional? Actually, it is not just simple install Kubernetes on virtual machines and give it to the user. You need to enable persistent volume provisioners. You need to have load balancers, cluster scaling, and all of these things. We provide them. For control plane, we use such project as Kamaji. Kamaji actually allows you to run your control plane components like API server, controller manager, scheduler, and connectivity as simple pods. So you can run your control plane components as pods, and then you can create virtual machines and join those virtual machines to this created control plane. The logic is the same. Kubernetes is the same Helm chart application, which creates set of resources managed by other operators. For example, if you create such resource like Kubernetes application, it creates cluster, Kamaji control plane, KubeVirt cluster, machine deployment, KubeVirt machine template, and KubeAdm config template. Those entities are managed by various providers in terms of cluster API. So Kamaji control plane managed by Kamaji control plane provider, the KubeVirt cluster and KubeVirt machine template managed by KubeVirt infrastructure provider, and KubeAdm config template managed by KubeAdm bootstrap provider. Actually, the logic of this is bootstrap provider out of KubeAdm config template create a secret for virtual machine which has KubeAdm join command with a token which allows you to run, if you run virtual machine with this cloud init configuration, it will just simply join to the Kubernetes control plane. While machine deployment is pretty similar resource in KubeVirt, it actually creates machine set and machine, and this machine is actually managed by KubeVirt or any other cluster API operator. In our case, we use KubeVirt because it allows you to run virtual machines as pods in your cluster. And what about multi-tenancy? So we were constructing our system with design that user have no access to management cluster. User can have access to their own tenant Kubernetes clusters. They can request load balancers, persistent volumes right from this, but have no access to the controllers managing this. So all of these controllers are running outside of the tenant Kubernetes cluster. They can order PVC, for example. They will magically appear in their cluster, but they will not see controller communicating with management Kubernetes cluster. So the main logic was that user can access only their provisioned services or order new services through some middleware, for example, website or your billing system. For now, we changed this logic a little bit, so it allows you to also to give user access to the Kubernetes API of management cluster. So they will have this dashboard where they can order the services. If we talk about multi-tenancy, we implement such model like Unix way, if we can say. By default, we have tenant root, like root user in Linux, but every tenant also have specific domain assigned. So for example, tenant root can have example org, and if you create new tenant, you can create them hierarchically. So you can create new tenant, for example, tenant foo, it will get new subdomain as name of tenant to this default domain, and the next tenant also will create another subdomain that is used for automatic configuration. So if you create, actually all the tenants are particularly Kubernetes namespaces, and if you deploy some applications inside of these namespaces, they automatically get a host name for accessing these services according to the tenant host name. Also, we re-implemented Linux kernel namespaces in terms of tenant isolation. That means that you can have tenant root, which holds these kind of specific services like etcd for storing Kubernetes, monitoring hub, ingress, and also we have cvdfs for S3. Every time when you create new tenant, you can say if you want to have them isolated etcd or monitoring or this kind of services. If you run tenant without isolation, so you can create tenant without isolation by monitoring, the applications running in this tenant, they will automatically configure to use monitoring of upper tenants. Yeah, by default, the tenants from the top always have access to tenants in the bottom, but tenants from the bottom have no access to tenants in the top. So in this way, you can simply create the scheme when you have one organization with single Grafana, and you can have isolation by developer teams. They can have separate services running and still have access to the same Grafana. This might be really convenient and allows you to save resources if you don't want to have separation by etcd or monitoring. You can actually run everything in tenant root and still have isolation between the users. So finally, we got the scheme where all our environments are unified and reproducible. We have simple installation to try for our users. Our platform covers all the infrastructure stack needed to build your own cloud. It is easy to extend, and we are open source. Come to our GitHub project and give stars. I will provide you links to the projects mentioned in this presentation. The first one is Talos Linux. The second is our platform. Of course, Kamaji, which allows you to provision Kubernetes control planes, and the set of my articles on kubernetes.io, which describes how the things work. And if you're interested in commercial support, feel free to contact us. We will provide you all type of services for building your own cloud.